Assalamualaikum. So today my group 5D want to present about MEMS. There are 4 people at my group, which is Muhammad Afiq bin Muhammad Rodi, Muhammad Khairi bin Muhammad Kusairi, Nur Farhana binti Zulkifli, and Zarif Haziq bin Izhar.
Introduction of MEMS. In general, MEMS, known as microelectromechanical system, is a process technology used to create tiny integrated device or system that combine mechanical and electrical component. MEMS is also the integration of mechanical element, sensor, actuator, and electronic on a common silicon substrate through a microfabrication technology. Okay, does that mean that MEMS is important to us? Well, MEMS do offer us the opportunity to produce mechanical, electromechanical, and electrochemical device with the same unprecedented level of miniaturization and functionality as a modern, very large-scale integrated, or as known as VLSI. Does that mean that MEMS is important to us? Well, if you can take a look at the right side of the slide, you can see a car that we use we usually use. The application of MEMS do use a lot from just a car. So without our realization, we do use MEMS in our daily life. So I can say that from here, MEMS is important for us.
Assalamualaikum. My name is Zarif Haziq bin Izhar. Today I want to present about the story of MEMS. In 1961, first silicon pressure sensor demonstrated. In 1967, invention of surface micro machine. Westinghouse creates the RGT, description of use of certification material to free micromechanical device from the silicon substrate. In 1970, first silicon accelerometer demonstrated. In 1979, first machine inject nozzle. In 1992, MCNC start MUMPS sponsored by the ARPA. Also, first micro machine Heinz. Next, 1993, first surface micro machine accelerometer sold. In 1994, did reactive ion etching is patented. Next, 1995, BioMEMS rapidly developed. In 2000, MEMS optical networking component become big business. In 1982, dispensable blood pressure transducer. Also, silicon as a mechanical material, and LIGA process. Next, in 1988, first MEMS conference.
So for application of MEMS, there are 5 fields of work that use MEMS application. First is automotive, for example, international navigation sensor. Second, airbag sensor. Third, fluid level and vapor pressure sensor. And lastly, air conditioning compressor sensor. Second field of work that use application of MEMS is electronic. For example, disk drive heads, inkjet printer heads, projection, screen television, and lastly, mass data storage system. For medical, the example of application that use MEMS is blood pressure sensor, masker stimulator and drug delivery system, implanted pressure sensor, and lastly pacemaker. The fourth application that use MEMS is communication. For example, voltage control oscillator, which is VSCO. Second, splitter and couples. Third, tunable laser. And lastly, projection display in portable communication device and instrumentation. Lastly is defense, for example, data storage, aircraft control, arming system, and lastly, munition guidance.
Future trends. There are a few points for future trends related to MEMS. First one, access to foundries. MEMS companies today very limited access to MEMS fabrication facilities or foundries for prototype and device manufacture. The majority of organizations expected to benefit from this technology currently do not have the required capabilities and competencies to support MEMS fabrication. Next, design, simulation, and modeling. Due to highly integrated and interdisciplinary nature of MEMS, it is difficult to separate device design from the complexities of fabrication. Consequently, a high level of manufacturing and fabrication knowledge is necessary to design a MEMS device. Furthermore, considerable time and expense is spent during this development and subsequent prototype stage. Next, packaging and testing. The packaging and testing of device is probably the greatest facing the MEMS industry. MEMS previously described that packaging presents unique problem compared to traditional IC packaging in that a MEMS package typically must provide protection from an operating environment as well as unlimited access to it. Next, standardization. Due to the relatively low number of commercial MEMS devices at the pace at which the current technology is developing, standardization has been very difficult. To date, high quality control and basic forms of standardization are generally only found at multi-million-dollar investment facilities. However, in 2000 progress in industry, communication and knowledge sharing was made through the formation of a MEMS trades organization. So the last one is education and training. The complexity and interdisciplinary nature of MEMS require educated and well-trained scientists and engineers from a diversity of field and background. The current numbers of qualified MEMS-specific personnel is relatively small and certainly lower than present industry demand. Education at graduate level is usually necessary, and although the number of universities offering MEMS-based degrees is increasing, gaining knowledge is an expensive, time-consuming process. Okay, so that's all for future trends of MEMS. Thank you.